Good morning, students. I hope you all are doing well at home. You all are safe. We are now moving ahead to the next unit of your syllabus. The next unit is Unit 3. We have completed 2 units. Just a reminder to you all. The first unit was electrostatics and the second unit was current electricity, which has been completed along with the solved ICSE numericals. We are now proceeding to the next section, that is magnetic effects of current and magnetism. Right now we will be dealing with magnetic effects of current. Magnetic effects of current, it's a very simple concept which we have dealt already in class 10. The concept is that whenever there is a current passing through a conductor, it creates a magnetic field around it. Alright, that is called magnetic effect of current, and the branch of physics that deals with this magnetic effect of current is called electromagnetism. Now, if anything has been stated, means it has been already proved experimentally also, and it was first proved by the scientist Oster, and the name of the experiment is very commonly known as Oster's experiment. And how was the experiment conducted? The setup was very simple. He just took a conductor. Right now it is not carrying any current. In order for it to carry current, you will put some variable resistor, that is the rheostat, to control the current, and it was connected to a cell along with a key. And to see whether magnetic effect has been created or not, there is a device called magnetic needle which will detect the presence of magnetic field. Now if you have a magnet, you put a needle around the magnet, the needle will start getting deflected, right? Here also what he did was, he took a magnetic needle. Initially the key was off, there was no current flowing in the circuit, and he took a needle. Do you think there will be any deflection right now? No, because there is no current flowing through it and there is no magnetism induced. Now once the key has been plugged in, that means the circuit will be closed now. The direction of flow of current will be from positive to negative. So just above the needle, the current is flowing from this side to this side. Now what Oster saw in his experiment was that the needle deflected, the north pole of the needle deflected towards the west. Now to see if there is any change in the direction or the nature of magnetic field because of the change in the direction of current, what he did was, he just changed the terminals of the battery. If he did this one, what happened? The direction of current was reversed. Now the current will be moving from right to left above the needle, and he saw a change in the deflection of the needle. The needle deflected this way. That means north pole of the needle deflected towards the east. So it is evident from these two setups that whenever there is a current flowing in a conductor, there is a magnetic field produced in the vicinity of the conductor, and that effect is known as magnetic effect of current. And on changing the direction of current, the direction of deflection of the needle changes, which means that the direction of the magnetic field also changes. So this is all about Oster's experiment to verify electromagnetism. Now, if there is magnetism produced, there is something called magnetic field. We know the term field means the space around a magnet or a current carrying conductor in which the magnetic effect can be felt. That is called magnetic field. You keep a magnet on the table and how far can the effect of that magnet be felt? That is called magnetic field. Alright, I hope the basics are clear to you. We will now move on to a very important law in magnetism, that is called Biosavards Law. Now it was stated by two scientists, Bio and Savart. And what did they state? They stated a law which deals with the amount of magnetic field produced due to a current carrying conductor. Suppose you have a very long current carrying conductor of, say the current is from south to north, and you take any point P here. Now this P lies in the vicinity of this current carrying conductor. That means there will be a magnetic field induced at this point P. The amount of magnetic field induced in this point P is given by the law Biosavards law. For that, we will just complete the diagram. Say the line joining this current element, the length of which will be equal to dl, will be assigned a vector sign. Say the point P and dl, they are making an angle equal to theta, and the position vector of this point P from this element dl is equal to r. Say we have got a small current element AB. Now Biosavards law does not give you the total magnetic field at P due to this entire wire. It gives you the magnetic field only because of a very small current elements. Now naturally when you just integrate the magnetic field due to these small current elements, you will be getting the total magnetic field. So first we will be taking small elements at a time, and later on we are going to integrate it. So that is it regarding the diagram. Now what does this law states? It states that the magnetic field induction dB, we are taking dB because we are taking a very small current element due to which the magnetic field induction will not be a very big value. So small magnetic field induction at the point P, dB is proportional to, not one thing here, there are three things which will decide the amount of magnetic field induced at the point P. The first point is dB is directly proportional to I. Here I means the current flowing through this current element. Okay, so if the amount of current flowing will be more, naturally the amount of magnetic field induced at the point P also will be more. That is natural, right? So this is the first factor. The second factor stated by Biosavards law is that dB is directly proportional to the length of the current element. Longer the element you take, the amount of magnetic field induced will be greater. That is natural. You take a long portion, here the magnetic field induced will be more. Thirdly, we'll talk about the angle here. dB is proportional to angle sine of the angle between this current element and the position vector r. These are the three factors which all are proportional to each other. Now the fourth factor talks about inverse square law in physics. You know, inverse square law means if you increase the distance, the value keeps on decreasing. Like your gravitational force, if the distance is more, the force gets reduced. Like magnetic force also, magnetic field also here, magnetic field induction at the point P is inversely proportional to the square of the distance between the current element and the point P. These are the 4 factors which help you to find out the magnetic field induction at any point P at a distance r from a current element of length dl. The angle between the current element and this will be equal to theta. Now, to sum up, because it is a statement, it has to come down to one line. We are just going to combine all these 4 equations. Combining all these 4, you will be getting dB is proportional to I dl sin theta divided by r square. So we have combined all the 4 factors to get a single expression here. dB is proportional to I dl sin theta by r square. Now we need to take this sign of proportionality out. So we will introduce a constant term here. So replacing proportionality sign by equal to sign, a constant k will be introduced here. I dl sin theta by r square. Now we will, to find out the value of k, that is a constant, we will take 2 systems into consideration. The first system is the CGS system. In CGS system, it's very simple. The value of k comes down to be 1. So in CGS system, dB will be equal to 1 into I dl sin theta, that is I dl sin theta by r square. And in SI, system, the value of k is mu naught by 4 pi I dl sin theta divided by r square. So here is a new term, new constant that you have come across, mu naught by 4 pi. Here mu naught is called the permeability of free space. Like we had epsilon naught in electrostatics, here we have mu naught. I hope it is clear so far. So in CGS, this will be helpful when you solve the numericals. If all the details are given in CGS system, the value of k, you need not worry, it's equal to 1. Expression simply write down as I dl sin theta by r square. And in SI, the value of dB is mu naught by 4 pi I dl sin theta by r square. You have to now get used to this mu naught by 4 pi. I hope it is clear. So Biosavards law, the expression I will be telling you in SI only, it is mu naught dB will be equal to mu naught by 4 pi I dl sin theta by r square. Now in vector form, the same law can be written in vector form also. dB in scalar was mu naught by 4 pi I dl sin theta by r square. Alright. Now if I want to write this in vector, you know sin theta denotes cross product between 2 vectors. Now which 2 vectors? Here you have to take this theta into consideration to know the 2 vectors here. Suppose you have A cross B. How do you write this in scalar form? It is AB sin theta. Now what is this theta? Theta is the angle between A and B. And here you have I dl sin theta to be written in vector form. Now what is this theta? The angle between dl and r. Alright. That means sin theta, in place of sin theta you need to introduce dl cross r. Since you have introduced this r here, it has to be divided here. So dB, I'll put a vector sign because now I am writing the vector form of Biosavards law. dB is equal to mu naught by 4 pi I dl cross r, because theta is the angle between dl and r, divided by r cube. Now this is the vector form of Biot-Savarts law. I hope it is clear so far. So you need to know these two expressions in scalar form and in vector form. Now if it is a vector, it needs to have a direction, right? The direction of this dB will be determined by the vector law. How you used to find the direction between two vectors? You can either use the right hand screw rule or you can use the right handed rule. How to find the direction? It will be in a direction perpendicular to the plane containing dl and r. You have to imagine a screw, okay? Since it is dl cross r, the screw has to be tightened from dl till r, and when you do so, the direction in which the screw goes, whether inside the plane of the board or paper or outside the plane of the paper, that will be the direction of dB. Now, as I told you, Biot-Savarts law gives you the magnetic field induction at a point P because of a very small element. What if I want to find out the magnetic field induction, not dB now, B, because of this entire length of the wire? To do that, you will just find B will be the integration of dB, which again will be equal to, I'll take the scalar form, mu naught by 4 pi. You need not integrate this because it is a constant. Current also will be a constant for a given wire. So integration, r square also will be a constant. Integration dl sine theta. This is how you find out the total magnetic field at a point P because of this entire length of the wire. Alright, we will now move on to the application of Biot-Savarts law. The first application is to find out the magnetic field due to a straight wire carrying current. Alright, so let us take a straight wire, the length of which may be infinite. We will come to the special cases later on, okay? Then say you have a point P at which you are finding out the magnetic field induction due to this straight wire. I'll name the wire as XY, alright? And to apply Biot-Savarts law, I need to define a very small current element, the length of which will be equal to dl. Okay, now from dl I will join this midpoint of dl till p, the angle for which will be equal to theta, and you can see there is one more angle there. I will take this angle as phi. Later we will have to focus on this angle only. We are going to find out a term in terms of phi. Alright, and the perpendicular distance between the midpoint of the wire C till this point P is taken as A, alright, and the position vector here is R vector. Okay, let's start to find out the magnetic field induction at the point P due to this wire XY. Applying Biot-Savarts law, dB will be equal to mu naught by 4 pi I dl sine theta by r square. Alright, now here what will be the total current flowing? If the total current flowing in this entire length is I, then the current for this small element will be equal to IDL. So I will consider this as the current element IDL. Alright, let me take this as equation 1. Now we will have to reduce some of the terms or find out some terms in these known terms, like in terms of a which is fixed, alright, in terms of phi which will help you to integrate later on. So let's proceed that. Let me take angle, triangle POC. It is a right angle triangle, as you can see, right angle triangle POC or PCO. Okay, you can see here theta plus phi is equal to 90 degree, isn't it? Because here I have drawn the perpendicular line, so this angle will be equal to 90 degree. So naturally theta plus phi has to be equal to 90 degree, because sum of all these angles has to be equal to 180 degree. Then, or I can write theta is equal to 90 degree minus phi, and we had sine theta here, alright. So what I can write is sine theta is equal to sine 90 degree minus phi. Now sine and cos are complementary, so sine 90 minus phi will come down to cos phi. So I have come down to an expression from theta to the angle phi. So sine theta will be equal to cos phi, which we will be replacing it in equation number 1. Now let's proceed to other terms here. I hope it is clear. So what I can write is sine theta is equal to cos phi. Let me keep it separately now. Now, if you again look at this triangle, I will take cos phi is equal to A divided by R, because cos is base by hypotenuse. This is our base and this is our hypotenuse. Now what I am trying to do here is I am trying to find an expression for R in terms of phi and A. I told you A and phi are known to us. So R will be equal to A divided by cos phi. I hope it is clear, you are getting it. So this has to be again replaced in this expression. We have R square here, so I will again write it here. R is equal to A divided by cos phi. Now one more variable that we have in this diagram is dl. We don't want the expression in terms of dl because it keeps on changing, alright. So for dl, let me take tan phi. Again taking the same triangle, tan phi will be equal to L divided by A. So what will be my L? L will be equal to A tan phi. But we don't have L here, we have DL. So how to find DL from L? Just differentiate it. So after differentiating, you will be getting DL is equal to A. Differentiation of tan phi is sec square phi d phi. So I have got one more term here, dl is equal to a sec square phi d phi. Hope it is clear. Now I have got three terms here which need to be eliminated from this expression. So let me replace all these three in this equation number 1. So I will get dB is equal to mu naught by 4 pi remains there, I remains there, my dl is a sec square phi d phi. I am writing it here. Okay, I can rub it from this side. I will continue. A sec square phi d phi and sin theta is cos phi by R. R is A by cos phi. Because we have R square here, I will write A square and this cos square phi will go up here. So directly I can write it as cos cube phi. You know sec phi and cos phi are just reciprocals of each other. So we will be just left out with dB is equal to mu naught by 4 pi I. A gets cancelled here, I by A remains here, sec square and cos square reciprocals, they cancel out. So I will be just left out with cos phi, and of course we have d phi. So this is the expression for magnetic field intensity at a point due to a long current carrying conductor. We are not done yet. We need to find out the total magnetic field. To find out the total magnetic field, you need to integrate within certain limits. So total magnetic field will be equal to integration dB. We had P here, dl was here, r was here. Okay, this was theta, this was phi. Now the limits, since I told you it might be an infinitely long wire and we are integrating with respect to phi here, so we need to put the limits in terms of phi, and we have limits from minus phi 1 to phi 2. Okay, so the integration limits will be equal to minus phi 1 till phi 2. Rewrite dB. You will get mu naught by 4 pi constant, I by A constant, integration minus phi 1 to phi 2. My dB was equal to cos phi d phi. Now integration cos phi is equal to sin phi, so it is mu naught by 4 pi I by A, integration is sin phi, you need not put plus c because we are doing definite integrals, minus phi 1 to phi 2. After putting the limits, you will be ending up with the expression mu naught by 4 pi I by A sin phi 1 plus sin phi 2. So this is the value for the total magnetic field intensity due to the entire length of the wire. I hope it is clear to you. Then your task will be to take two special cases. The notes have been posted to you. One case you are going to take is if the conductor is of infinite length, then you have to take phi 1 and phi 2 both equal to 90 degree. Okay. And the point P lies near the center of the conductor, that is case 1. So here you just need to take phi 1 and phi 2 both equal to 90 degree. Find the expression yourself, and if the conductor is of infinite length again and P lies near the end. The first case was P was lying somewhere here, and the second case is P will be lying either here or here. So in this case, one of these angles will be equal to 90 degree and the other one will be equal to 0 degree. You find out the expression and you can send your assignments to me. Thank you.